All right, so my demo didn't work, so I don't really have anything to show, but I'll try to keep it interesting. Before I get started, how many of you have heard of Ray before? All right, how many of you have heard of Kubernetes? I'm just kidding. So my name is Abdel. I'm a developer advocate. I live in Stockholm, and I co-host this podcast called the Kubernetes Podcast from Google. If you're not a subscriber, I will give you 2 minutes or something. I'm not going to do that. I work on everything Kubernetes mostly, and Ray is one of these interesting frameworks that started kind of bubbling up 2 years ago. It came out of a research project. Initially, the project itself was actually a research project out of the University of Stanford, which the people that built it, they were trying to build a Python-based HPC framework. So they had nothing to do with machine learning to start with. And then eventually, they open sourced it, and eventually, a lot of cloud providers started being interested. And now the people who actually built the framework, they left, and they created a company called Anyscaler. So they're the only big cloud provider out there that provides Ray managed on top of virtual machines or Kubernetes or whatever. But because Ray is open source, and because you can pretty much run it anywhere, it's obviously a good fit for Kubernetes, and that's what we're going to talk about today. And so why? Because doing distributed computing is cool, and that's pretty much what everybody's doing today. And because also Python is sort of like the main language for everything AI today, right? So Ray is written in Python because most machine learning engineers and data scientists actually use Ray anyway, day-to-day, to write their own code. The thing with generative AI today is that you cannot do distributed computing as an option. It is not an option anymore, right? Let's take a very simple example. DeepSeek, which is one of the newest models that kind of created a lot of noise when it came out. The biggest model is 678 billion parameters. If you run that model at quantized 8 or 16, let's say just 8, you need 1,200, give or take, gigabytes of VRAM. There is today no GPU in the world, single GPU, that has 120 or 1.2 terabytes of VRAM, right? So in order to run Ray, or to run DeepSeek on top of Kubernetes or on top of a VM, you actually cannot even use a single VM anymore, because there is a physical limitation on how many GPUs you can put in a single virtual machine, and that physical limitation is typically 8. If you take the biggest GPUs that exist today, which is the H200 from NVIDIA, they have 80 gigabytes of memory, maximum. So that's the biggest GPU you can get. So I'll let you do the math of figuring out, like dividing 80 by 1,200 and figuring out how many GPUs, and therefore how many nodes. So the TLDR, this long introduction, is just say, distributed computing is a must. Like, you cannot go without it. Why? Scalability, availability, efficiency, flexibility. The problem with distributed computing is what you all know, that once you run things in more than one computer, you're calling for problems, right? Fault tolerance, stuff will break, security concerns. These are all challenges that you probably have already dealt with today. And so what is Ray? Ray is a Python-based framework that is trying to basically solve an end-to-end life cycle of machine learning with a single framework. Today, if you're a data scientist or a machine learning engineer, you're probably using 1, 2, 3 frameworks. You're using PyTorch, you're using some transformers you're using one framework to do training, you're using one to do like fine-tuning, you're using another model to data process process the data that you will use to train the model, et cetera, et cetera. Ray is trying to give you that end-to-end one framework to do everything. It's built on this layered approach, where Ray itself comes in 2 layers. There is Ray core, which is the core of the library. So that's the command line and basically the basic libraries. And then there is a set of libraries that's run on top of Ray core. Everything on top is optional. You don't have to use any of that stuff. You can use Ray, for example, to run a model, the Ray serve part. And then you can use any other library from any other framework that you're already used to. Or you can just use Ray for everything. When you are actually importing Ray into your requirements.txt file as a Python, you can import Ray or import Ray brackets, data, rlib, fine-tune, whatever. So you can import either the entire thing or just a subset of the libraries. At the bottom, we have the cloud layer, and that's basically where your code will run. As far as people who built Ray, they are trying to keep it as agnostic as possible. They don't care. They don't really care too much about Google, AWS, or Azure. From them, as long as you have a VM or a container, Ray will run, right? So this is kind of like, if you are in the data scientist world, this probably slide speaks to you, because these are kind of like the popular frameworks that exist today that you can use to do the same thing that Ray does. So let's take about, for example, for serving, you can use something like Grady or Fast API. If you are doing fine-tuning, you have MLflow. If you're doing training, you have XGBoot, TensorFlow. Hugging Face also have their own libraries. So you can use any of these. You can mix and match, or you can just use Ray for everything, right? And so where does Kubernetes comes into the picture? Well, basically for the rest of us, for those who are platform engineers, people doing platforms, the layer that you care about is all the bottom part, right? That's the thing that Kubernetes give you, which is consistent API, same API works everywhere. If you would use Ray with virtual machines, you will have so much variability because the way virtual machines on Google work are different than the one on EC2, are different than the ones on Azure. Kubernetes gives you that standard API for running everything. If you're a platform engineer, it gives you also the possibility to run stuff for your teams and have them not care too much about where stuff runs. So all they do is they have their Jupyter book, they use their own third-party libraries to write their own code, and then run it on Kubernetes, and then it will just run. And that gives you possibility to do it on Google Cloud, AWS, Azure, or if you're crazy enough, on-prem. So I will just like steer the discussion a little bit toward one topic, and we'll go back. If you are doing Kubernetes today, and you have used the job API, you know that the job API in Kubernetes is very stupid. Because the way it works is that it allows you to write a job, right? And then define certain behaviors. If the job fails, retry a couple of times, and that's it, right? There is no concept of priority. There is no concept of resource sharing. So if you have multiple teams, let's take a very simple example. Kubernetes pods have a priority concept, right? Like you write priority, and the scheduler will take that priority into account before scheduling the pod. If you have 5 teams running their jobs on top of Kubernetes, and you tell them that please be nice and set the priority to a reasonable amount, how many do you think will actually set the priority to a reasonable amount? 0, right? Everybody will set the highest possible priority. So to go around this, we introduced this project called Q. It's open source, and it's used actually by a lot of companies, including CERN. Ricardo is not in the room. So the way Q works is that it allows you to define what we call local queues or cluster queues, and those are basically the way you would define resource utilization. So if you have 10 GPUs, you can define them in a cluster queue, and you say these 10 GPUs has to be used by team A, team B, and team C on specific policies, either time or if, let's say, for example, you have serving framework, you have a serving model, and then you have a fine-tuning job. And what you want to do is you want to set your serving to be highest priority, because if you have a chatbot that depends on the serving, you need that model to be running all the time. But then you can also say, oh, when there is no traffic coming through my website and the serving job kind of scheduled down, then I will run the fine-tuning job because I don't care about the fine-tuning job, right? So with Q, you can do all these kind of things. And what you can do is you can combine Q with Ray to manage jobs through Q. There is also one more thing that was introduced recently. It's called multi-queue. Q works on a single cluster level. If you want to do Q across multiple clusters, there is something called multi-queue, which allows you to define what we call a config cluster. The config cluster has all the configuration and all the policies, and then your users submit their job to that config cluster, which then decides which other clusters will run the jobs. This is very interesting for if you don't have enough GPUs on-prem and you want to scale out to cloud, right? Or the other way around. We also have this reference architecture. If you're interested, you can scan the QR code. There is 2 versions or 2 flavors. There is one which uses Ray only for the data processing part, and then it uses PyTorch for fine-tuning and VLLM and GPUs and the gateway for the serving. And there is another version which uses Ray for everything. So these are both reference architectures with code and configuration and everything. They are designed to run on GKE, but you can pretty much run them on any Kubernetes cluster anywhere. And then you have all the code, all the reference architecture, if you want to see how you could use Ray for end-to-end machine learning. As I said, you can run Ray anywhere. They have this thing called VM Launcher, which essentially allows you to run Ray on top of VMs. But they also have something to run on Kubernetes, which is what we care about. And that thing, we call it KubeRay. So KubeRay is an operator on Kubernetes that allows you to run Ray on top of Kubernetes. Why Kubernetes? I don't want to spend too much time on this. You already know why we care about Kubernetes. The way KubeRay works is that it introduces 3 new CRDs, one called Ray Cluster, one called Ray Job, and one called Ray Serve. You use these CRDs to define your job, whether it's so the first obviously one is Ray Cluster. So Ray itself has a concept of cluster and has a concept of control plane and data plane, right? So if you are installing Ray, you would typically have at least 2 nodes. One node acting as they call it head or the control plane, and then one node or multiple nodes acting as your worker node. And in order for you to submit a job to Ray, so to send something for Ray to process, you will just use a command line to send stuff to the control plane, which then run it on top of the worker nodes, right? And if you are already familiar, this is kind of the similar architecture of Kubernetes, right? Control plane, data plane. Ray cluster is a CRD that allows you to define a cluster on top of Kubernetes. So you create an object called Ray cluster, you define how many, usually you only have one head node, so one control plane, 3, 4, 5, 6 data planes, and when all of these things get provisioned, they are running as pods, right? So if you do a Ray cluster, define it, run it, kubectl gets pods, you will see as many pods as nodes that you have in your Ray cluster. Ray job is the same idea. You can just use it to run a job, right? So it's kind of like an abstraction layer on top of the job API in Kubernetes. Under the hood, it will create a job API, and it will create a pod. But you just use Ray as a higher level definition. If you don't define, so when you are defining a Ray job, you can actually either let it automatically create a Ray cluster, or you can just tell it to run on top of this existing cluster. So if you already have a Ray cluster provisioned in your Kubernetes, you define a job, and you say in the job, this is the IP address of my head node, and then that job will get sent to that Ray cluster to run on top of it. Ray serve is the same thing. It's just basically to serve a model, right? Ray by default uses VLLM under the hood, but they are actually working open source upstream to try to make it agnostic. For now, it's only VLLM. So if you want to run, if you write a Ray service, and you execute it in the cluster, and then you go kind of dig into the pod, it's just VLLM container, right? So there are a few interesting things with Ray when you start using it. I started playing with it like a year ago, and I helped quite a lot of customers on it. And so one of the things I realized very quickly when I started working with it is in the documentation of Ray itself, they always talk about this thing of ephemeral versus persistent clusters. And the recommendations from the people who wrote Ray is to always do ephemeral clusters, to never do persistent. Because they say if you have persistent clusters, things can be unpredictable, and you will not know why. There are multiple reasons why you would want to do ephemeral or static. First of all, what is ephemeral or static? Well, essentially, do you create one Ray cluster and then run all jobs on top of it? Or do you create one Ray cluster per job, right? So the first one would be static. The second one would be ephemeral. Running ephemeral gives you reproducibility. So for each job, you create a new Ray cluster, and that's essentially easy to reproduce. If that cluster fails or the job fails or whatever reason, you can easily rerun the job to kind of figure out what went wrong, right? It gives you also, there is no need for maintenance. Like no one needs to keep Ray clusters running around, so it's pretty easy to manage. And it gives you kind of better observability. On the con side, startup can be long because you need to wait for the cluster itself to be provisioned before you can run anything on top of it. And one more very interesting thing for people who are in the observability space, Ray itself does not have a way for you to ship logs and metrics outside of the cluster. So if you create a Ray cluster, run a job, the job generates logs, if that cluster gets deleted, everything goes away. So you have to figure out on your own cloud platform, how do you can get like the logs and the metrics shipped out. If you are using something like Google Cloud, we have an agent that essentially read logs and then push them to Google Cloud Ops. I guess AWS and Azure have the same thing. Or if you're using something like Datadog, you have to make sure that the Kubernetes cluster has the agents deployed to be able to keep the logs, right? Same thing for persistent. Persistent gives you better latency for starting your workloads because the cluster will be just running there all the time. It's probably more work for you if you're a platform engineer, and less work for you if you are a data scientist or machine learning engineer. But the problem with persistent clusters is that they need maintenance. Ray itself has versions, and if there is a new version of Ray coming with some features, you will be, as the platform engineer, responsible for updating the cluster for your users, right? So there are pros and cons for each. You kind of have to evaluate which one works better for you. The very important thing about Ray is that Ray doesn't give a damn about security. It has no concept of security. All the endpoints of Ray are opened by default. The dashboard doesn't have authentication, and it doesn't have authorization. So the moral of the story, don't put this thing on the internet. Unless you want somebody to figure out what's your endpoint for your cluster and start running jobs on top of it and then costing you money because GPUs, right? So if you are running on top of a cloud provider, you can try to figure out if that particular cloud provider has a way to, for example, put a load balancer in front of your API endpoint and then build in some sort of authentication or authorization mechanism. But by default, Ray doesn't have any of this stuff. Actually, if today you go install Ray, the CRDs, on top of Kubernetes, and then create a Ray cluster, you can simply do kubectl port forward and then load the dashboard. The dashboard is read-only, it doesn't allow you to do anything, you cannot click through it, you cannot do much from the dashboard, but you can see what that would be a problem. If the dashboard is fine, the API endpoint itself, so the dashboard is port 8265, and the API endpoint is port 1001. So if you port forward 1001 and have Ray command line installed, you can just do Ray job submit to that API endpoint, and the Ray will just accept it, because it doesn't have a concept of authentication authorization. So this is something to keep in mind. It's growing quite a lot. The community behind it is pretty big, and there is quite a lot of adoption. I know at least one or two of these biggest AI providers today that use it, but I cannot tell you the names. You could probably infer it from context, because two of them are customers of Google Cloud. But there is quite a lot of adoption, and people are using it. I will talk about a couple more things that are coming in the Kubernetes space that you will be hearing about quite a lot that I think are interesting to keep an eye on. There is this thing coming in Kubernetes called DRA. It's actually already in 131 alpha, and I think it's coming out of alpha to beta in the next version. So it's the 134 or 135, I don't remember. DRA stands for Dynamic Resource Allocation, and it's essentially a mechanism in Kubernetes to optimize the provisioning or those hard-to-obtain hardware, so GPU, TPU accelerators, all that stuff. So it's a way in Kubernetes where essentially instead of treating a pod that requires a GPU as static in the sense that you need to provision the pod first, provision the node, make sure the node has the GPU, install the drivers, and then run the pod on that particular node, which in my opinion kind of goes against the whole philosophy of Kubernetes, because you want basically Kubernetes to be able to schedule the pod wherever it finds resources. So DRA is a new API that allows you to define all these resource requests, and I am putting resource requests between quotes because they're not resource requests in the sense of the request you put on a pod. They are a different type of API that basically allows you to say, I want this configuration of a node. And you don't have to provision the node upfront. Once you put the pod on the cluster will automatically use DRA to provision the underlying hardware, right? So keep an eye on it, it's pretty interesting. And then one more thing, which also is interesting in the context of general stuff, but it's interesting in the context of Ray. I don't know how many of you know, but in Kubernetes 1.27, there was an introduction of an alpha feature that allows you to live resize pods, right? So now you can kubectl patch the requests section of your pod and just add more CPU and more memory, and the pod will resize live, right? Today, it's 1.27 was alpha, and I think it's beta now. And this works, right? This exists today. So you can basically, if you have a Ray worker or a Java workload, and you need to resize it, it will be possible. What we are doing is we put in a KEP, Kubernetes Enhancements Proposal, to contribute to VPA, which is Vertical Pod Autoscaler, contribute live resize of pods without restarting them as part of VPA. So this feature came out at 127, right? We built like a CRD operator type thing that no one is using because it's kind of stupid to have one operator just for this particular task. And then we decided finally we're just going to make it possible through VPA. So the new version of VPA, which is VPA stands for Vertical Pod Autoscaler, right? Today, Vertical Pod Autoscaler has to restart your pod. If you have a VPA object pointing at a pod, and then your pod utilization, resource utilization goes above a certain levels that you define in the VPA itself, it will just kill the pod and create a new one, right? You can use VPA in what we call recommendation mode, because VPA has a field called auto, and if you turn it off, it's not going to restart the pod, but if you do kubectl describe on the VPA object, it will tell you what resources you should put on the pod. It will recommend the size of the pod, right? But we're making it possible for VPA now that you can do multiple things. Obviously, live resizing pods without restarting them is a good one. But the second one, which is very interesting for me at least, is CPU boost. You will be able to actually say, configure VPA to say, target this pod using selectors, right? And then you can say CPU boosted for 120 seconds, which means that if your pod requires 4 CPUs, and then you say CPU boost this twice for 120 seconds, at startup and during the first 2 minutes, your pod will have access to 8 CPUs. And this is very interesting for, again, Java workloads, because Java workloads tend to require a lot of resources at startup time, and then they kind of go down. You don't want to over-provision the pod because you will be wasting resources. So with CPU boost, you'll be able to say, OK, artificially boost this pod. It's not actually artificial. It's technically physical. Just boost this pod for a certain amount of time or until the pod is ready. We tested it. So we have the code actually written. We just need to get the KEP, the Kubernetes Enhancement Proposal, accepted so we can contribute to upstream. But the test I have been doing, I could get like a Spring Boot app to start 3 times faster with CPU boost.
That's going to be a whole lot of fun on licensed software.
Yes, yes. So that's a whole battle of war I'm not going to open right now. But yes. But on cloud, so the thing with CPU boost actually is that a lot of cloud providers already offer it today as part of their proprietary platform. So if you're using ECS or Fargate, or if you're using Google Cloud Run, you have a button that you can click, and then it will give you CPU boost out of the box. You pay for it, obviously, but this exists. So what we're doing with this is just making it possible in open source Kubernetes. I'm not going to talk about this. This is all I had today. I hope it was useful. And if you have any questions, I'm open to answer them. There is, I think, one question there.
Hi, Kabi.
Yeah.
Hello. Yeah. First of all, thank you for the talk.
Thank you.
It was awesome, and I'd like to know more about Ray now. But yeah, the question is about actually for the vertical pod autoscaler. Do you know if there's any plans for making the boost available for some event basis? For example, when HTTP request comes in, then give some boost for like 2 minutes for some pod, and then fall back to the default autoscaler limits or stuff like this.
So the KEP that is opened doesn't have that. What I would encourage you to do is go find it. Like you can find the enhancement proposal and just write a comment if you think that that's something interesting for you.
Yeah.
But that's actually a very interesting use case. So you have an event-based system, and you want to, when you have a lot of messages, to like double the size.
Yes.
Why would that? Okay, would autoscaler work for this case, like HPA, like horizontal pod autoscaler? Because you can do HPA on custom metrics, right? So you can autoscale a pod based on custom metrics. As long as you are able to get those metrics out of whatever platform that sends you messages, you can configure an HPA to say, you know.
Yeah, I'm aware of that, but I'm specifically interested on the single pod use case, just boosting vertically, and also leveraging those Kubernetes new feature of not restarting the pod to scale the resources up and down.
Got it.
Down dynamically. That would be awesome.
Yeah, I think the KEP that we have open source doesn't, but the tool that I told you that we open sourced is actually in GitHub, so you can go look it up and see if this would work. So Kube Startup CPU Boost, this is the operator that we wrote, that we open sourced, that basically does, so this is the before VPA, right? This works today. Yeah. It would probably require you to turn on, are you on some cloud platform?
Google.
Okay, so you will have to create an alpha cluster. Yeah. But I can show you a quick, this is how it looks like. So this is the first version that we wrote, and you can see there, it's a CRD called Startup CPU Boost, right? This is your selector. So this is how you select the pod you want to target. And this is the resource policy. So we say here, increase the CPU by 50% up until the pod is ready. We can also do time-based. We can also like specify fixed resources, right? And we can also do time-based CPU boosting. So we can do 60 seconds or 120 seconds, whatever, right? So go look into this and see if this is something that could be, I most probably require some rewriting, but it could be used. It's written in Go. So
absolutely, thank you.
Well, of course.
Thank
Any other
you.
questions?
More questions?
Either I was very, very clear in my presentation, or no one have an idea what I was talking about the last 30 minutes. Yes.
How would you compare Ray with Kubeflow?
Oh, interesting. I think
How would you compare Ray with Kubeflow?
Yeah. How do you compare Ray with Kubeflow? Kubeflow doesn't do everything that Ray does. So it doesn't have serving, I think. And it doesn't have any data processing libraries. So Ray can do all the stuff that Kubeflow can do and then more. And then with the Ray operator, actually there was a discussion at some point to instead of maintaining the Ray operator as a standalone operator, to like integrate it into Kubeflow, because Kubeflow have an operator for Kubernetes. So if you're using both, you don't need to install 2 operators. But I'm not quite sure what their discussions kind of led to. But yeah, thank you.